Right, so today we're going to continue review the remaining chapters. So chapter 18, we talk about acid base. Right? So mainly weak acid base because strong acid base, they completely dissociate, right? So there's nothing much we need to worry about. But for weak acid and weak base, because they partially dissociate, right? So the mass become more complicated. And so in this chapter, we mainly learn these important definitions or these terms, right? So this KW, proton hydroxide concentration, pH, pOH, right? So make sure you know the relationship between them, right? And also for weak acid and weak base, there's a Ka value, Kb value, which is the acid dissociation constant and the base dissociation constant, right? So we can use the relative value of this Ka and Kb to determine the strength of the acid and base. And so when we're talking about how to classify the strong acid, strong base, or weak acid, weak base, if you have the K value, right? So if you have the K value, it's more straightforward because the value, the magnitude of the K value can basically tell us whether it's strong acid or not, right? So make sure you know how to calculate, right, all these terms. Kw again is equal to 10 to the negative 14 at room temperature. So that's the water ionization coefficient, right? So that means the concentration of hydrogen, proton, and hydrogen is ion, right? Proton. So I normally write the proton as this instead of H3O plus, right? Actually, most people write proton like this. Right? So the concentration of proton times the concentration of hydroxide, right? They always equal to Kw. Kw at room temperature is equal to 10 to the negative 14, and it changes when temperature changes, right? So meaning that at room temperature, if you know the proton concentration, you can calculate the hydroxide concentration, right, using the Kw. And in terms of pH or pOH, right? So every time you add a p, lowercase p in front of term, the p means that you want to take the negative log of that term. Right? That's a negative log of that term. So pH is the negative log of proton concentration, and the pOH is the negative log of proton concentration. So if we take the 10 to the exponent on each side, so we can have proton concentration equal to 10 to the negative pH. Right? So similarly, the hydroxide concentration will be 10 to the negative pOH. Right? So make sure that you know how to calculate all this. Right? So normally, if you given one of this, you should be able to calculate the rest. And the next thing is compare. By comparing the strengths of acid and base, we can find the reaction. We can find the reaction direction between the acid-base pairs. Right? So if you have an acid-base pair, you can find the reaction direction, right, based on their strengths. And the last is predict the property of a salt solution, right, based on the cation and the anion. So we will talk about that in more details later. So the chart we're gonna use most often for this chapter is the one on the right, right? So this table here, it lists the relative strengths of the acid and the base, right? So for each pair, you have the acid and its conjugated base, right? So basically, you get rid of the hydrogen to get the conjugated base. So for the acid, the acidity increases from bottom to top, and for the base, the basicity decrease from top to bottom. Right. So when you have say a weak acid and weak base, generating another weak acid and weak base, right? So you don't know which direction this reaction is preferred, right? It could be this way or this way, right? So when you see a problem like that, you can base on the relative position, right, in this table, right, which is their relative strength. The rule is that you want the stronger acid and base produce the weaker acid and base, right? So in this case, I will compare the strength of the acid on the left and the acid on the right. Right, so for H2S is here, ammonium H4 plus is here. So in this chart, I see H2S is a stronger acid than ammonium. Right, so because we want stronger acid to produce weaker acid, so this reaction, right, is preferred to the right. Or it means that if you mix the same concentration of everything here, the Kc is Kc should be greater than 1. Right, so if it's at equilibrium, the Kc is gonna be equal to 1, right? But if it's preferred to the right hand side, right, so that's greater than 1. And say, so on the other end, if this reaction is reversed, that means the Kc will be less than 1. Right, so you can also get the same conclusion by comparing the strength of the base. Right, so for ammonia's here and the HS minus here, right? So because the base is stronger at bottom, so ammonia is stronger than HS minus. So that means the reaction is going to proceed to the right. Right, so notice that this table doesn't include all the acid and base, right? So when you see a problem, ask you which acid is stronger, they will have several rules to follow. Right, so first we compare the when we have acid that has a proton connected to a nonmetal, right? So for example, the halides. Right, so in this case, we're gonna compare the electron negativity of these nonmetals. Right, the rule is that for hydrogen halides, right? So the higher the electron negativity, the weaker the acid. Right, fluorine is the one with the highest electron negativity. That means when it's covalently bonded to this hydrogen, it doesn't want to get rid of this proton. So it's very hard to break free. So the acid is going to be very weak because its ability to donate that proton is weak. And for hydrogen iodide, because iodine is less electron negative, that means it's easier for the proton to be donate free. So the acid is stronger. Right? So this is for hydrogen nonmetals. Right? So, but when you have oxy anions, right? For example, like ClO4, right? Or BrO4. Right? So this is called oxy anions. Right? So when you have acid like this, the rule is that when the number of oxygen atoms are the same, you compare the electron negativity of the nonmetal. So the higher the electron negativity, the stronger the acid. Right? So in this case, chlorine is more electron negative than bromine, so this is a stronger acid. Right? So when you have the same nonmetal, right? So when you have the same nonmetal but different oxygens, right? So for example, HClO4 and the HClO3. Right? So you have same nonmetal but different number of oxygens. The higher the number of oxygen, the stronger the acid. Right? So there's more details about why in the video lecture. Okay, so let's work on an example. So we have this acid is a weak acid but stronger than the other weak acids, right? Because based on the pKa, right? So pKa is 2.87. That means the Ka is equal to 10 to the negative minus 2.87. Right? So normally when I see a Ka that is 10 to the negative 3 or even lower, I just assume this is a very weak acid, right? And so you can make an assumption that the percent dissociation is going to be small, which again is going to simplify our math. And so in this problem, right, so we got a K value based on the pKa. Right? So we put the acid into water. So this is the initial concentration. So that's the only thing we added at the beginning. Right? So we have 0 concentration of the product. And notice that you have the equal concentration of the proton and its conjugated base of the weak acid. Right? So the change, we represent that with x, all the coefficients of 1, so we don't have a multiplier here for the x. And the water is liquid, so we don't worry about it. So this is the equilibrium concentration. Right? So again, the K value is equal to proton concentration times the concentration of the conjugated base divided by the concentration of the acid. This is the concentration at equilibrium, right? Because this is a K, right? K is the equilibrium. So this numbers goes in here, right? So not the initial, right? So this numbers goes in here. So we can solve for this equation. But again, because we have made the assumption that this percent dissociation is going to be small, so the X is going to be small compared to the initial concentration, right? So we can assume that 1.25 minus X, which is the denominator, is approximately equal to 1.25, meaning that it barely changes, right? So this equation becomes this. So it's a much easier equation to solve. So after solve for X, we got 0.04, right? So every time you make an assumption, you must justify it, right? The way you justify is you divide this X by the initial number, which is in this case 1.25. You multiply 100% and see whether this percentage is greater or less than 5. And if it's less than 5%, like in this case we have 3.3, that means our assumption is good. Right? So, but if it's greater than 5, that means the assumption is not good. So you must use this equation here to solve for X. Okay, so now because X is the proton concentration at equilibrium, you got this, and then you take the native log of it. So that's the pH. So for in this slide, you have two example problems, right? The first is determine whether the Kc is greater than 1 for these two reactions, right? So these reactions are between weak acid and base, not necessarily weak, right? So again, the rule is, right? So if a reaction prefer to the right, it is Kc is going to be greater than 1, right? So if it prefer to the left, Kc is going to be less than 1. Right, so let's just find their position in the table and compare their strengths. Right, so for HCl and the ammonium, these are the acid. Right, so HCl is here, ammonium here. So HCl is stronger, so the reaction prefer to the right. So Kc is greater than 1. Or you can, if you want, you can compare the base. Right, so base is here, chloride is here. So this is a stronger base. Right, so reaction proceed to the right. So for the second one, you have H2SO3, and you compare that with ammonium. Right? H2SO3 is here. It's also higher than ammonium, right? So it's a stronger acid. So this reaction also proceeds to the right. For both of them, Kc is greater than 1. Right? So remember, for the acid, the higher, the stronger. For the base, the lower, the stronger. Okay. And the next problem is determine the property of the solution, salt solution, right? Based on the cation and the anion, right? So in this case, when we have, say, the conjugated acid of a strong base, right? So this is a conjugated acid of strong base, and this is Br is the conjugated base of a strong acid, right? So when they're both strong, the solution is going to be neutral, right? The reason is that none of these ions, when they dissolve in water, none of them is going to react with water, right? So the solution will remain neutral. But when we have a conjugated acid of a weak base, right? For example, ammonium ion, right? Ammonium ion is a conjugated acid of a weak base right here. So the iodine is the conjugated acid of a strong acid, a conjugated base of a strong acid. And so here we have a weak base, anion of a weak base, and anion, a cation of a weak base, and anion of a strong acid. Right? So in that case, the solution is gonna be acidic because the iodide by itself, right, it doesn't react with water. But for this ammonium, it reacts with water, generating proton. Proton is acidic, right? So the pH is going to be less than 7. And so when we have a compound that has a conjugated acid of a strong base, right? So potassium's conjugated acid, strong base, but a conjugated base of a weak acid. Cyanide is here. Let's see. So it's a conjugated base of a weak acid. Right, so in this case, the solutions become basic. Right, so the solution is going to become basic because, right, the potassium doesn't react with water, but the cyanide here, right, the cyanide by itself is gonna react with water, generating HCN and the hydroxide. Right, so hydroxide will make the solution basic, so the pH is gonna be greater than 7. Right, so the last case is when you have a cation and anion of a conjugate, both weak acid and base. Right? So for example, let's pick this. So ammonium cyanide. Right? So they're both from weak acid and weak base. So in this case, we have to compare their relative Ka and the Kb value. Right? So whichever dominance will show the corresponding property. Right? So if Ka dominance is gonna be acidic, if Kb dominance, that's gonna be basic. And chapter 19, we cover 3 topics. Right? First is buffer. Second is titration. Right? So titration between acid and base. And the last is solubility, right? Or the precipitates. Right? So acid-base titration. So for a buffer system, right, it must have this common ion effect. Right? So normally, for a system to act like a buffer, it should have a weak acid and is a conjugated base. Right? So normally it's a mixture of a weak acid and it's a conjugated base. So you need both. Right? So when both of them present, right, the common ion will be this conjugated base. Right? So it will show a buffer. It will show this buffer effect. So a buffer basically reduce the change of pH when strong acid and strong base is added into the system. Right? So without the buffer, the pH is going to change dramatically because the acid and base added is strong. Right? But when you have a buffer system, the pH change is going to be small. Right? So when you have a buffer system and you want to calculate the pH, you can always use this equation, right, which is this one. Right, so which is equal to the pKa of this acid plus the log of the ratio of the base divided by the acid. Okay, so again, you can only use this equation when you have this conjugated pair of acid and the base. Okay, so next is titration between acid and base. So we've done a lot of problem on that, and make sure you know how to draw this titration curve if this key information is given, and also from a titration curve, what valuable information you can get. Right, so we're gonna look at more examples later. And the last one will be the solubility of a salt of a compound. Right, so based on the solubility to determine whether it's gonna the salt is gonna be precipitate or not when dissolved in the water. Right, so let's look at one by one. So first we have this acid-base titration. So this titration curve represents the titration between strong acid and strong base. And so between strong acid and strong base, right, as we learned last semester, they're gonna produce water and the salt. That's meaning that the proton and the hydroxide is gonna react completely. Right? So in this case, the titration is based on the same number of moles of proton and the hydroxide, not their concentration. Right? So you want the same number of moles and the proton and hydroxide, where you should use M1V1 equal to M2V2, right, to do the titration problem. So when you require to draw a titration curve, if you're given some data, remember you have to put pH on the y-axis, right, the volume of titrate added on the x-axis, label the units, right? Also, one important point is the equivalence point, right? The equivalence point when the mole of protons equal to the mole of hydroxide. And for strong acid and base, the pH is equal to 0. Right? For weak acid with strong base or weak base with strong acid, right? So the pattern looks similar, but there's some difference. Right? So the major difference is that when you start with a weak acid or weak base, you're gonna generate a buffer system when the equivalence point is reached. Right? For example, in this case, when you start with a weak acid adding strong base, right? So for this weak acid, right? So when you add a strong base, which is hydroxide, right? It's gonna, this hydroxide is gonna completely react with this weak acid and generate this conjugated base and water. Right, so as long as this weak acid is not all consumed, you're gonna have a mixture of this unreacted weak acid and the conjugated base that generated. So you're creating a buffer system because they have the common ion fat. So before the equivalence point is reached, you have this buffer region, and yes, you can see the pH increase. Right, it takes a lot of base, right? Take a lot of hydroxide to be added to reach the equivalence point because, or to change the pH, right? Because it acts like a buffer, right? So in this buffer region, there is an important point, which is called the halfway to equivalence point, right? So that's the middle of this buffer region. And the reason that is important because the pH at this point is equal to pKa, right? Because pH is equal to pKa plus log base concentration divided by the acid concentration in this case, right? So in this case, when it is a halfway to the equivalence point, that means 50% of the starting weak acids has been reacted. So you have 50% left, and that 50% that is reacted become this conjugated base, right? So you have the same concentration of base and acid. So the ratio here is equal to 1. And we know that log 1 is equal to 0. So this term becomes 0, so pH equal to pKa. All right, so if you do experiments, measure the pH, and plot this graph here, you can estimate the pH at this middle point, and that will give you the pKa of the acid. Right, so when it is at equivalence point, that means the number of moles of hydroxide added. And the number of moles of hydroxide added is equal to the number of moles of the weak acid that originally exist. Right, so again, the moles equal. Right, so now all the weak acid become its conjugated base. Remember, the number of moles are equal, but the concentration is not equal because when you add sodium hydroxide, the volume change, right? So the mole stays the same, but the volume change, so the concentration also change, right? The concentration will be changing, right? So do not use the same concentration, right? You have to consider the volume change to calculate the new concentration for this conjugated base when it is at equilibrium. Right, so when at equilibrium, when at equivalence point, the pH, when you count the pH, you can no longer use this equation, right? Because all the acid has been consumed, you have a denominator 0, so you can no longer use this equation anymore, right? So you only use it when you have a mixture of these two. But if one of them is being all consumed, you can no longer use this equation, and that is a very common mistake that I detected in the exam 3. Like a lot of you still use this equation at the equivalence point, right? So that is wrong. To calculate the pH at the equivalence point, you have to base on the concentration of this concentrated base generated, right? So after you get the new concentration for this concentrated base, right? So this conjugated base will react with water and generate HPr and hydroxide. And based on the amount of hydroxide generated, you can calculate the pH at the equivalence point. All right, so for the titration between weak base and strong acid, the similar thing applies, right? So you have a buffer region at the beginning. Right? So in this case, in this buffer region, you're gonna have unreacted ammonia, but also the conjugated acid, the ammonium ion, right? So you have a buffer, right? So the calculation is same as the case for weak acid and strong base, but the trend is different, right? So here the pH decrease because you add strong acid. And the last part is the solubility problem, right? So for example, when you add some say calcium hydroxide solid into water, you want to see how much is dissolved. Right? This is a barely soluble compound. Right? So you want to know how much ions are generated, right? So this is related to the solubility of this compound. Or the other way, say if you mix this cations and anions, right? So you want to see whether you can produce a solid or not, right? So for both type, we can use this QSP and the KSP to solve the related problem, right? So for this reaction, right? So for the solid to dissolve into its ions, right? So the QSP is equal to the concentration of the metal, right? In this case, the calcium. And you have an exponent. The exponent is the coefficient. For calcium here is 1, so this P is going to be equal to 1. And X is represent the anion, which is the hydroxide in this case. Right, so because it has a coefficient of 2, so Q here is going to be equal to 2. Right, so when this systems are equilibrium, the QSP is going to be equal to KSP. And at that case, we said the solution is saturated. Right, so it's right at saturation, so no change is going to happen. But when QSP is greater than SP, that means that the allowed, like this aqueous phase concentration is higher than the solubility or than the maximum allowed concentration. That means you're gonna generate more precipitate. So it means the reaction is gonna proceed to the left, which means you're gonna generate more solids until it reaches saturation. Right? But if you have a lower concentration of this dissolved phase, right? So QSP less than KSP, that means it hasn't reached saturation yet. So no precipitate will form. You can keep adding both of one of them, right? So or both of them, so until you see the solid form, right? So that's when QSP less than KSP, right? So there are no precipitate form. So when you see a problem like whether it's gonna precipitate or not, right? You just compare the QSP with KSP, right? And if you have a KSP value and you want to know how much calcium or how much hydroxide is generated, right? You can use this equation, right, to solve it. So first, let's look at an example of a buffer-related question. Right, so for a buffer system, again, you need to have common ion effect. Right, so in this case, we have this propanoic acid. Right, so we use this HPR to represent it, and the common ion is the PR minus. You cannot introduce PR minus by itself, so normally it's come with a salt. Right, so it's sodium salt NaPr. Right, so that's what we added here. Right, so the sodium propanoic. Right, so this is a sodium salt. So the amount we added, right, so completely dissociate into sodium under the PR minus. Right, so meaning that at the beginning, the concentration for both, right, is equal to 0.35. Right, so when you list this ICE table, right, so the equation is acid react with water, right, become its conjugated base and the proton. Right, so this scenario is different than the example problem we did in the previous chapter. Right, for that one, we only have the acid. We don't have any conjugated base added. But in this case, we started by adding some conjugated base also, right? So the approach is same, right? So you use ICE table to find their equilibrium concentration. And again, for this weak acid, because the K is small, so you can assume X is small. So you can make this term equal to 0.35, make this term equal to 0.15. And the Ka is given, so you can solve for X, and the X is gonna be 5.6 times 10 to the 6, right? So that's equal to X. So again, you have to justify this, right? So you divide this by a 0.35 or a 0.15, right? So you get the percentage, which is say way less than 5%. So meaning that this assumption you make are good. Right? So then X is the proton concentration, so you can convert that into pH. So you got 5.25. Right? This is the most accurate to solve this. Right? So another way to solve this, and this is easier, is using this Henderson-Hasselbalch equation. Right? Because we have a buffer, right? So with the buffer system, we can use this equation directly. Ka value is given, so we can calculate pKa. Right? Again, if you know the Ka, pKa will be the negative log of a Ka value, right? That gave you the pKa. Right? So we know the base, right? The conjugated base is 0.35. Right? The acid is 0.15. Right? So we can use the equation directly. So you get the same result. Okay. But remember, right? If any of them is 0 or is not buffer system, do not use this equation. The next example problem is related to the solubility. Right? So here it asks for the molar solubility, which basically asks here the amount of metal that dissolve from the compound. Right? So here we compare the solubility in pure water and when there is a common ion effect. Right? In B, when you add this ISR nitrate, this nitrate is all soluble, right? So that becomes SR2 minus and the 2 nitrate. Right, so you start with 0.13 molar of SR2 plus already. Right, so in part A, when it's in pure water, right, you got no product at the beginning, so S at equilibrium. So because this is solid, so we don't have it in our equation, right? So KSP is given, is that this? So it's actually equal to S squared. Right? So we can solve for X. So this is the molar solubility in pure water. And in B, right, the difference is that instead of having a 0 concentration at the beginning, we have 0.13. Right, so the KSP expression become, instead of S squared, become 0.13 plus S times S. Right, so in this case, because this KSP value is small, we can assume that 0.13 plus S is approximately equal to 0.13. So you can simplify this equation into 0.13 times S. Right, so you can solve for this S and get the result. And again, you have to divide this number by 0.13, right, to justify. So times 100%, and it's gonna be less than 5. Right, so you can see that when you have a common ion effect, the solubility, right, decreased significantly, right? So earlier you have -5, here you have -9. So chapter 20, we go to the thermodynamics, right? So the first thermodynamic term we learn is delta H, right? The enthalpy in chapter 6 last semester. In this chapter, we introduce 2 more thermodynamic terms. Right? First is this enthalpy, entropy, right? And then we introduce free energy. And this is their relationship. Right? The free energy is equal to the enthalpy, right, minus temperature in Kelvin, is in Kelvin, times the entropy. Right, so first we introduce S, right, entropy. So that's basically the degree of freedom. Right? The more freedom of the system, right, more gases, right, the more microstates, right, the more combinations, and more freedom, right, the higher the entropy. Right, so delta S is a final entropy minus initial entropy. Right, so that's a state function. So for a chemical reaction, right, so we can also calculate the delta S for a chemical reaction, which we're gonna talk about in the next slide. Right, so we can also relate the delta S with the delta H in the system under surrounding using this equation. Right, so then we talk about how to determine whether a reaction or a process is spontaneous or not based on the sign of delta S universe, which is basically the second law of thermodynamics. Right, so the second law of thermodynamics says for all the spontaneous process, we had the delta S universe must be greater than 0, right, meaning that the sum of the delta S system plus delta S of surrounding must be greater than 0. Both of these terms have signs. So for process to be spontaneous, their sum must be greater than 0, which is the second law of thermodynamics. Right, so we can calculate the delta S of system, which we're going to talk about later. Right, so the delta S surrounding is actually equal to this. So the delta H of the system divided by T with a negative sign. Right, so we're going to look at the example problem using this equation later. Right, so the next term we introduce delta G. Delta G is called the free energy. Right, so the free energy of the system can be also related to the spontaneity of the process. But the thing is that we want this delta H to be negative for this process to be spontaneous. Right, so because this delta H is calculated based on delta G is calculated based on delta H and the delta S, so you have 4 different combinations, right, based on the sign of delta H and delta S to determine the sign of the delta G, right? So based on their sign, we can determine whether the delta G is spontaneous or not. So we can calculate whether it's spontaneous or not, right? So the last part in this chapter is that when we have non-standard states, so we have non-standard state, how to calculate the free energy, right, based on the standard free energy and the reaction condition. And also we can correlate the equilibrium constant of a reaction with the standard state free energy. So earlier we talked about how to calculate the delta S of the system. Or if this system is a chemical reaction, that would be the delta S of a chemical reaction. All right, so as standard state, we can use our friend appendix B, right, to calculate the delta S of a reaction. So if you have a chemical reaction, so you just have to find the sum of the entropy for the products, and minus the sum of the entropy for the reactants. Right, so just find the spaces and find the corresponding standard entropy. Right, take the sum of the products, take the sum of the reactants, subtract them. And this is the same way we calculate the heat of the reaction, delta H of the reaction. And similarly for delta G, right, you can also use this same form of calculation. Right, so for delta H, right, you can use this heat of formation. For delta G, right, you can use free energy of formation. And for delta S, you can use this standard entropy. Right, so they're all the same equation, right, just different terms. And to determine whether a reaction is spontaneous or not, right? Earlier we talked about use the sign of a delta S universe, right? But we can also use the sign of a delta G. Right? So, but their chain is different, right? So for spontaneous reaction, the delta S universe greater than 0, but the delta G is less than 0. Right, so keep that in mind. Right? So you want a positive delta S universe or negative delta G for a reaction to be spontaneous. Right, so when they're equal to 0, that means the reaction is at equilibrium. Right, so you can actually figure out that which temperature, right, this sign of delta G is going to change, right, based on the relative ratio of delta H and delta S, right? So because when you want this delta G equal to be 0, that means delta H is going to be equal to T times delta S, right? So you can find out at which temperature this delta G is going to change sign. Right, so this last gives us the equation to calculate the free energy, the non-standard state free energy, right, with given reaction conditions. That is the delta G without this nod, right? So that's the delta G without this standard state notation. So it's equal to the standard free energy plus RT times natural log Q. Q is the reaction quotient, right? So if you're given a mixture of reactant and products, you know their concentration, so you can calculate the reaction quotient and plug in into this equation and calculate the delta G. And for the standard delta G, again, you can use appendix D, right, to calculate it. And at standard state, the delta standard free energy delta G now is actually equal to minus RT, right? Minus RT natural log of K, right? So that means at equilibrium, right? So this standard free energy, right, is related to the equilibrium constant of the chemical reaction, right? So if this is given at the temperature, you can calculate the standard delta G. Or if you know the reaction, you can use appendix D to calculate the standard free energy, and you can figure out the equilibrium constant. So let's work on a example problem. So this one is based on the sign of delta S universe to determine whether the reaction is spontaneous or not. Again, the delta S universe equal to the delta S of reaction plus the delta S of the surrounding, right? So we have to know both of this. So for delta S of reaction, we use appendix B, right, to calculate. We know this reaction we're talking about, right? So this is our system, right? So this is a delta S for the products. This is the sum of the delta S of the reactant. So we got the delta S of the system or the delta S of the reaction. Right, so for delta S of surrounding, again, we use this equation. Right, so to calculate the delta S surrounding, we need to know the delta H of the reaction. The temperature is given here. So all we need to do is use appendix B to find the delta H of the reaction. Right, so we use a heat of formation, right, to find the delta H. So this is the sum of the delta H of the products. This is the sum of the delta H of the reactant. So we got delta H of the reaction divided by temperature. We got the delta S of surrounding, which is this. Right, so we add these two together, we got a positive number. So a positive delta S universe, meaning that the reaction is spontaneous. This example problem related to the delta G, standard delta G equilibrium constant. And also when we have non-standard state, right? So what is the free energy when we have a reaction mixture? Right, so first in part A, right, so we know the K value is given in the problem. So we can apply this equation directly to calculate delta G because temperature is given and the R is a constant. So we got the delta G. Remember, the sign of delta G can also help us determine whether the reaction is spontaneous or not. And because this reaction is written in this way, and the delta G, right, the standard delta G is greater than 0. Greater than 0 means it's non-spontaneous, right? So meaning that this reaction to the right is not preferred, but this reaction is preferred to the left. Right? So if you reverse it, you switch the sign, so that delta G will be negative. So the reaction to the left is actually preferred. All right, so part B, if the standard state concentration of the reactant and products are mixed, right? So that means everything equal to 1 molar, right? So for aqueous phase, standard state is 1 molar. So meaning that the Q is going to be equal to 1. right? So that doesn't, so when Q is equal to 1, natural log of Q is also equal to 0. So meaning that it doesn't change the delta G. So it's still non-spontaneous. I still prefer to the left. So it's still prefer to the left. And then C, we have a different concentration of right-hand products. So first we need to calculate Q, right? So remember the coefficients become the exponent for each concentration, right? So we get a Q value, we take the natural log of it times RT, right? So this is what we're doing here. And then we add that to the delta G. So we still got a positive number, right? So meaning that reaction is still not spontaneous, right? So, but if it's proceed to the left, it's gonna be spontaneous, all right? So last chapter is electrochemistry. So this chapter, we did a lab on this also, right? So first we talk about how to balance redox reaction using half cell methods, right? So make sure how to do that because you know how to do that because there's gonna be a problem on the exam, right? So we're gonna go over an example on this, right? So then we have discussed the composition of a electrochemical cell. So we mainly talk about this voltaic cell, which means the reaction is spontaneous, right? So once we close the circuit, right, so everything should happen spontaneously. We also talk about, right, the cell potential, which is the overall cell potential, which is calculated based on the half cell potential. And in each half cell, we should have an electrode, the electrolyte solution, and when we connect them, we need a circuit, we need a wire, right? We also had a sub-bridge. And by convention, right, we write anode on the left, cathode on the top. Anode is where oxidation happens, right? So an ox, right, red cat. Oxidation happens at anode, reduction happens at cathode. Right? And later we talk about how to use appendix D, right? So appendix D is the relative redox potential for each metal pairs, or the individual metal reduction potential, right? So based on that, we can compare the reactivity or the strength of the metal or the reactivity of the metal, right? Based on the relative position in the table, which is react based on the redox potential. Right? At the end, we correlate delta G, E cell, and the equilibrium constants, and also find the non-standard state cell potential, right? Find the E cell at non-standard state, right, using the Nernst equation. Right, so for electrochemical cell, if I ask you to draw it, right, so you again, by convention, they put anode on top, so you have to tell me, right, the oxidation happens here, the half cell reaction, and the cathode is on the right, so this is where the reduction happens, and also give me the overall reaction, and I also want to show the flow of the electron from anode to cathode, and also in the sub-bridge, the flow of the anions and the cations. In terms of the notation, right? So we also talk about the notation for electrochemical cell, right? Because you don't want to draw this every time, right? It's too time consuming. Right? So using a notation, we can represent the electrochemical cell. We use this double vertical bar to separate each half cell. Use this single vertical bar to separate different physical states. Right? So on the left, we have anode. On the right hand side, we have the cathode. And we put the electrode on the outside. Right? We put electrode on the outside. And then you have different physical states. Right? So you need this single bar to separate them. And only those involved in this overall reaction is mentioned in this notation. Right? For example, in this electrolyte solution, you have a zinc sulfate. Right? Sulfate is not involved in this, so you don't have to put sulfate in this notation. And the cell potential is actually the difference between the reduction half cell potential on the cathode minus the half cell potential on the anode. As for zinc and copper, the standard cell potential equal to 1.1, right? So which is the difference between these two. and we use cathode minus anode, right? Remember that. You can, if you forgot, you can think about the electron flow, right? Because the electron flows from anode to cathode, right? So we're talking about this electric potential. So cathode is the destination. That's the final place, right? Anode the initial place. So we always do final minus initial. Right? So this is part of the appendix D. So in this table, give us a lot of information, right? We not only have the half cell potential, but we can also based on, because we rank the this reaction based on the relative half cell potential, right? Become more negative down below. So in this table or in appendix D, that means the metal here, right? So the metal or the this metal or this reducing product, right? So the more negative it is, the more reductive, or the higher, the stronger the reductant, right? So on the other hand, they're corresponding oxidant, right? So meaning that the higher their position or the more positive, right, this half cell, the stronger the oxidant, right? So this will be the strongest oxidant. This is the strongest reductant. This is the weakest reductant. This is the weakest oxidant. So based on this, we can basically compare the reactivity of different metals and see whether they can replace hydrogen from acid or replace a hydrogen from water. Right? So if this metal, right, is below this equation, that means they can, when you add it into water, you can replace hydrogen. And if this metal is below this equation, that means if you add these metals in the acid, you can replace proton from acid. But if you add this metal into water, it will no longer replace hydrogen from water, right? And for these metals, right, inert metals, if you add them into acid, they won't even replace the proton from the acid because they're above this equation, right? This equation, this zero potential, remember this is called standard hydrogen electrode, right? It's SHE. So the half cell potential of each half reaction is actually determined by pairing this, the one you're interested with this SHE, right? So we measure the potential at standard state. So this slide gave us the relationship between the half cell the cell overall cell potential with the free energy of the reaction and also the equilibrium constant. Right? In chapter 20, we know the relationship between these two. Right? So in this chapter, we can correlate these two, so we can correlate these two. Right? So these three, they have this relationship, and the relationship, the equation between each pair is shown here. Right? So that means that if you know one of them, you should be able to calculate the other two. Right? So in terms of the relationship between delta G and the E cell, right? At standard state, we have this equation. So at non-standard state, we can, this equation also applies, right? Have E. So we just get rid of the standard notation on delta G and the E cell. Right, so here N is the number of electrons being transferred, half is the Faraday constant, which is a constant. Right, so from chapter 20, we have the relationship between delta G and the equilibrium constant, so we can correlate these two. Right, so E cell can be correlated to equilibrium constant also. Right, so it's equal to RT divided by NF. R is a constant, F is constant, temperature is given. So at 298 Kelvin, we can simplify this whole term into this. Again, N is the number of electrons being involved. When you determine this, you have to look at the overall reaction. Right? So by simply looking at the half reaction, you probably get the wrong number of N, because, for example, in the equation earlier, zinc and the copper, right? In this equation, there are 2 electrons involved, right? So because copper donates 2, and zinc donates 2, and the copper accept 2. Right? But right? But some equations say, for example, you have zinc, I replace silver, right? So generating a silver metal and the zinc 2 plus. In this case, you have to balance the reaction, right? So yeah, although silver, from silver plus to silver, right, there is only one electron involved. But to balance this overall reaction, right, you need to multiply everything by 2. Right, so eventually there's still 2 electrons involved. Right, so that's what I mean by you look at this overall reaction. Right, so if you have a reaction that has 3 electrons involved, the other one has 2 electrons involved. To balance them, you have to multiply this one by 2, balance the second one by 3. So overall, there should be 6 electrons involved. So the n in that case will be 6. Right? So remember, right, these equations, right, you're gonna use it a lot, right, when in this chapter, for the problems related in this chapter. And the last one is the effect of concentration on cell potential, right? So that means when you have non-standard state, right, when the electrolyte solution is no longer 1 molar, right? So the cell potential is actually different than the standard cell potential. And you can use this Nernst equation, right? I mean this one, actually, the Nernst equation to calculate the non-standard cell potential based on the standard cell potential and the reaction coefficient. Right, so when this Q, right, is equal to 1, that means the cell potential is equal to the standard cell potential. But when this Q is less than 1, you have more reactant than the product. So this E cell is greater than the standard cell potential. Right, so when you have Q greater than 1, that means this E cell is less than standard E cell. Right, so you have more product than the reactant. Right? So for a reaction to be spontaneous, you want the E to be greater than 0, right? Because delta G is equal to negative NF E cell, right? So if you want the delta G to be less than 0 to be spontaneous, the E cell must be greater than 0 because you have a negative sign here. So when you have a voltaic cell, which means it's a spontaneous reaction, right? And you calculate the delta, you calculate the E cell, which is negative. That means you must got the cathode and the anode switched, right? So you probably want to switch them back. So let's work on a few example problems. So first one is the balancing redox reactions using the half cell method, half reaction method. Right. So if this is an overall reaction, and we have this acidic condition. Right. So notice this equation is not balanced at all, right? So we have oxygen on left hand side, we don't have oxygen. So we have to balance them using half reaction method. So we have to write down the 2 half reaction first and balance each half reaction and add them up. So first, let's find out the pairs, right? So first I have ClO3, right? So chlorate and the chloride. So this is the one pair here. So in here, I have the chlorine is a +5, chloride is -1, right? So it's being reduced, right? So this is where the reduction happens. So this is a reduction. And the other one must be oxidation, right? So aldehyde is -1, aldate is 0, right? So this is oxidation. Right, so first let's balance the number of atoms. Right, so your textbook says first balance the atoms that is not oxygen or hydrogen. Right, so in this case, we have one chlorine. Right, so the second reaction, we have 2 iodine here, but only 1 on the left hand side. So we put a 2 here. Right, so this second reaction, the number of iodine is balanced. Right, but for the first reaction, we have 1 chlorine, but the number of oxygen is not balanced. Right, so the rule says when we want to balance oxygen, we add water on the side that has less number of oxygen or has no oxygen. Right, so in this case, I will add 3 water because each water has one oxygen, right? I need to add 3. So I add 3 water. But adding water meaning that also adding hydrogen, right? So add 3 times 2 is 6. So I need to add 6 proton on the left hand, 6 hydrogen on the left hand side to balance hydrogen. And to add hydrogen, we add it in the form of proton, right? So we have to add another 6 proton on the left hand side. Right, so now we have ClO3 and 6 proton on the right hand side. We have chloride and water, but that's not enough, right? So because the charge is not balanced, yes, for both of them, we don't only want the number of atoms to be balanced, we also want the charge to be balanced. Right, so on this one, I have a -1 here, but +6 here. So overall, I have a -5. I have +5. So for on the right hand side, I have 0 here, -1 here. Right, so I have to balance the charge. So that means I have to add electron to the side that has a higher charge. So on this side, I have a 6 + 5. To make it equal to -1, I have to add 6 electrons. So I have to add 6 electrons. So now I have minus, so -5, be +5, -6 equal to -1. Right, so I add 6 electrons on the left hand side of the first reaction. And on the second reaction, I have -2 here. 2 times -1 is -2, and 0 here. So I need to add 2 electrons on the right hand side. So now I have -2 for both sides. Right, so now I have this 2 equations balanced in terms of atoms and the charge. Right, so each half reaction is balanced. But when we combine them to generate the overall reaction, we must cancel out the electron. Right? The electron being transferred must be equal. Right? So in the first reaction, we have 6, but the second reaction, we only have 2. So to cancel them out, so make sure we want to multiply the second reaction by 3. Right? So first, make sure they're on the opposite end. Right? So electrons in the first reaction is on the left hand side, and then on the second reaction is on the right hand side. Right? So we multiply the second reaction by 3, so that becomes this. Now I can delete the 6 electrons. So whatever left on the left hand side is this, whatever left on the right hand side is this. Sometimes you could have same terms but different coefficient on both sides. Right? So if that happens, you have to delete the one that has a less coefficient, and then adjust the coefficients on the other side. Right? For example, if you have 6 protons here on the other side, you have 10 protons. You have to delete this, and then you have 4 remaining on the right hand side. Right? In this case, we don't have that issue. Right? So this is our overall balanced redox reaction. Right? So you may start from this, and it becomes balanced like this. Right? So this example problem has 3 questions, right? So it pretty much asks us how to calculate the E cell, based on the standard E cell and the reaction quotient. Right, so first, let's identify which one is on the anode and which one is at the cathode. Right, so you can either use your common sense or use appendix D, right? So to search for those data spaces. So I know that for me, because I know that that cobalt, right? Cobalt is where the oxidation happens, right? Because cobalt is more reactive than nickel, right? So that's why I can just use these equations directly, right? Without thinking about which one happens at where. But if you know that, if you don't know that, you can use the appendix D, right, to see which one is lower, right? The one that is lower, that metal is the more reactive one, right? So in that case, cobalt is lower, so you have to write this equation by switch sides, right? So you want to change it into the form of oxidation, right, by switching the side. And for the nickel, so it remains as the reduction form, right? So The overall reaction by adding those two become this, right? So the cobalt is reduce nickel into nickel solid, and the cobalt itself become cobalt 2 plus. And the E cell, right, standard E cell is gonna be equal to the standard half cell on the cathode minus that on the anode. So the result is 0.03, right? So that's the standard E cell potential. That meaning that if both of this aqueous nickel and the cobalt is at standard condition, right, 1 molar, the reaction is gonna be spontaneous. So now we have E cells at standard state, but we want the E cell at non-standard state. So we need to find the reaction quotient. Right? So for this overall reaction, right, the reaction quotient will be equal to product divided by the reactant, right? So you have cobalt as the 2 plus as the product, nickel 2 plus as the reactant. And the number of electrons being transferred is 2. Right? So the cobalt concentration is here, and the nickel concentration is also here, right, given, right? So we can calculate that, got the E cell equal to 0.05, right? So which is greater than the standard E cell potential, right? So that's the initial E cell. That means it is greater than 0, so it is going to be spontaneous. Right? So it means that this reaction is going to proceed, right? And this voltage is going to decrease and decrease. Right? So part B asks us what is the nickel concentration, nickel 2 concentration when the E cell potential reaches 0.03, right? So part A, we just calculate that the standard cell concentration is equal to 0.03. Right? So when this E cell's potential is equal to the standard cell potential, that means Q is equal to 1, right? Based on our table earlier, we know that this Q should be equal to 1. Right? So meaning that when this Q equal to 1, the log of the Q is equal to 0. Right? The log of 1 equal to 0. So this whole term is going to be equal to 0. Right? So you want the cobalt concentration equal to nickel concentration. So at the beginning, the nickel concentration is 0.8, and the cobalt concentration is 0.2. Right? So that's the initial. And the change will be minus x, is the plus x. Right? For the amount of nickel being produced, for the amount of cobalt 2 being produced, that is the amount of nickel 2 being consumed. Right? So at the equilibrium, you have 0.8 minus x for nickel 2, 0.2 plus x for cobalt 2. So you want them to be equal, right? So you can solve for x is equal to 0.3. So for nickel, the concentration at this final condition will be 0.8 minus 0.3. So they use this equation. So when the potential is equal to 0.03, Q is equal to 1, and nickel concentration become 0.5. And the cobalt concentration is also equal to 0.5. Right? So that's also equal. And C asks us what is the equilibrium concentration. Right, so for electrochemical cell to at equilibrium condition, that means the E cell equal to 0, right? Because delta G equal to negative NF E cell. Right, so delta G is at equal to 0 means it's at equilibrium, right? So when this E cell is equal to 0, the delta G is also going to be at equal to 0. So means it's at equilibrium condition. So at equilibrium condition, right, the Q is going to be equal to K. Right, so in this case, we want this E cell equal to 0, right? So we want the left-hand side equal to 0. So that's going to be equal to the standard E cell minus this whole thing. So basically, you want this whole term equal to 0.03. So they all cancel out, right? So then you can solve for x. But in this case, right, you have equilibrium concentration of cobalt, right, 0.2 plus x equal 0.8 minus x, and then you solve for x, right? You take the log, I mean the 10 exponent of 10 on both sides, 10 to the exponent on both sides, right? So and you solve for x, and this x equal to 0.7, so you can get the equilibrium concentration. And you can see, right? So when at the beginning, right, you have a cell potential equal to 0.05, right? That when cobalt nickel concentration is 0.8, and the cobalt concentration it is 0.2. Right, so this is a spontaneous cell, the voltage cell, right? So reaction is spontaneous. So it's like using a battery, right? So after you use it for some time, the voltage becomes smaller, and the concentration of nickel decreases, right? And the decreases, and the concentration of cobalt increases. And when this cell died, right, is equal to 0, right, nickel concentration become even smaller, 0.09, and the cobalt concentration become 0.19. Right, so this ABC is basically tell you a story of how this battery died, right, after a certain time of operation. So that's all.